think we're ready to start our research plenary presentations. And our new research director, Randy Berry, will be chairing this session. So take it away, Randy.
All right, thank you, Nick. So we have five research talks by SpectrumX researchers. Just a reminder, we're 15 minutes per talk. Our schedule is pretty packed, so I think I'd encourage everyone to use the chat for Q&A. And I hope the speakers can respond to questions that appear in the chat. And also a reminder to the speakers to share your own screen and use your own slides. So with that, our first talk is going to be presented by Laila Marzall. So Laila, go away.
Can you hear me well?
Yes, perfect.
Awesome. Let me share. I am going to ask you guys that you put your questions on the chat because I have an in-person presentation at 3:30. Okay, so let me just, if I can move this, not very, okay, very nice with this one screen stuff. All right, can you see my screen, my full screen? Good? Yes? I cannot see
You're good.
anyone.
You're good, Laila.
Okay, thank you. All right, well, welcome everybody to my talk. Thank you for attending it. And I am Laila Marzall. I'm a research professor at CU Boulder, and I work under Professor Zoya Popovich, mentoring. I work for her lab, and today I'm going to talk to you about components and system level approaches for analog interference mitigation or suppression. So our main motivation is how we enable joint communication, sensing, and powering in RF3. And basically, let me just put the pointer here. It's going to be easier. And the main point is when you have a lot of users, you're going to have some problems with saturation because of interference. So we are going to talk about two approaches of our research. One of them is basically concentrated in the RF front end that are notch filters and circulators. And also I'm going to talk about the in aperture level interference mitigation. So our research topics, as I told you, are in tunable active circulators, active tunable filters, and self-calibration circuits for aperture level, interference mitigation. So this is the coexistence scenario, and here what you can see, it's a smart city when we would like to have, for instance, joint and sensing and communications, or joint power and communications. We have some phase arrays here feeding different users, and this leads to us, if they are working the same part of the spectrum, it will lead into interference. So basically what we're talking about here is about in-band interference that can come from yourself, from the PA in your transceiver, or from another user intentionally or non-intentional. So here we have, for instance, sources of self-interference. That's basically when your transmitter is talking too loud, so that your receiver is kind of getting deaf because of so loud that you were speaking. And from external sources, we have jammers and other signals, other users. All right. So how does that can translate downstream in a digital environment, from the RF to the digital environment? When you have, for instance, here the RF bandwidth, and you have signal 1, channel 2, channel 3, and you have a lot of interference, what happens is that your ADC starts to saturate, and that refrains or prevent the ADC to detect small signals, because in general the full dynamic range of the ADC will be compromised, not compromised, but basically will be saturated. So for that, what we have to do in the analog world to alleviate this problem is finding some mitigation tools. And what we have, for instance, to improve the self-interference problem, we can use some isolation, not devices, but circuits like switches and circulators, tapped filters, etc. And then from external, we can use some sort of beam shaping or digital filtering and frequency hopping. We're going to concentrate in the beam shaping. And when we want to use, for instance, two mitigation functionalities at the same time, we are going to pay something because some cost, because for instance, if you're going to do some beam steering, you're going to suffer from active impedance that is basically a variable load that will load or the switch or the circulators, and that will compromise isolation. So I'm going to explain a little bit of our research on that. So here, what you can see, the first, okay, I'm going just to minimize this and move this somewhere that I don't need to see. Yeah, it's not working. So here, what we see is like a schematic of what we call simultaneous transmit and receive in the analog domain. But the circuit can be also used for different channels, but in the same RF bandwidth. So here, what the parts that we are working on is on active tunable circulator and active tunable notch. And why is that? Because we want to use a shared antenna array, and this shared antenna array will transmit and receive. And as we transmit and receive and we steer this beam, that will load the circuit. I'm going to show some circuit topologies and the remedies that we are doing to mitigate this, this degradation in performance because of this other functionality that's phase arrays. The next approach that we are working on, if I can change the slide here, I'm not being able to change the slide. Okay, the aperture level simultaneous transmit and receive. In this case, we're considering two different arrays, one from transmit and one for receive. You still have some coupling in between them because you don't want to put them too separated from each other because that occupies space. So one thing that you want to do is like work in some calibration circuits. What you're seeing here is basically the data converters, and then some up and down conversion, analog beamforming, power amplifier, coupling to the LNA, and this coupling may compromise the receiving chain. Okay, so it started. I'm going to start here with the analog, the tunable circulator, and those are, this is basically one of the first approaches that we had in terms of integrated active circulators. What you're seeing here is basically a composition of amplifiers that will give you a first isolation in between input and output. So when you connect them in a type of delta connection, you can establish some initial direction of circulation. Connect to that, we have couplers, and the couplers, they help this performance by adjusting the phase in between the amplifiers. And what you can see, the results of this the circuit is that you are enabling some circulation, which means isolation in between the transmit and the receive, but also you can apply some gain to the path, what doesn't happen to just passive circulators. Extending this work, what we've done is with this topology, how we have one port that we can adjust internally. We propose tunable circulators. That's basically you use the fourth port of the couplers to apply some tunable load, and as the external ports, they change the impedance, you can retune the circuit to recover back isolation, gain, and matching. And here, what you can see are like the simulations of the circuit as we apply a uniform mismatch through all of the ports around a VSWR circle a little bit less than 2.1, and the behavior before tuning for isolation, that's pretty bad, and the recover after tuning from 3 to 4 gigahertz. Gain also improves from it recovers from the degraded state to the initial state around 7 dB of gain, and the matching also recovers. Continuing to the active tunable notch. Can you, hello, Francis, can you put yourself on mute? Okay, thank you. So in terms of active tunable notch filters, the topology, the concept is we have an income signal with some interference and some signal of interest. We split into, we have some variable gain and some variable delay lines in such a way that when you recombine this initial signal weighted, what you have is a deconstructive interference of the interferent signal, and still keeping the signal of interest in the same level or with some gain. This is one of the prototypes that we have. This mimic or microwave integrated circuit was designed and built in gas. In the wind gas PIH process, the total area is around 3 by 3 millimeters, 3.8 by 3 millimeters. And here what you can see is the simulated and measured result. And the most important part here is that you can observe is that basically input and output ports are pretty matched. And also the tunable notch or the interference point that we want to achieve has some tunability in between 8 and 11 gigahertz. And what we are doing right now in the seed fund project is scaling this structure to our F3 or 7 to 8.4 gigahertz. More about aperture level simultaneous transmit or receive. We would like to understand how the transmit path is coupling and how much interference we are getting to the receiving channel, so that we can use, sorry? Did you say anything? Because I'm not seeing anyone. Okay. So what we've done was Seth, one of our students, Zoya students, is designing some calibration circuits. That's basically, it is tapping some signal from the transmission path so that it can be treated or cancellated in the digital domain. A little bit more of information on this topology. What you can see here is basically the transmit side of a phase array with some tapping, and this tapping you have a switch and LNA that you can switch in between them, and then you transform to the digital information, and with that, and with the receive beamforming information from the ADC and the receiving path, you can do some digital canceling. So here is the mimic of the self-interference calibration circuit, and basically what you can see here is the mimic of the S21 parameters. That's basically the loss that it is seen here, and what we want is to reduce this loss as much as possible. And also we want to keep isolation in between the transmit observer to the receiver. So here we have the curves a comparison in between the simulated and the measurements of the chip. And this chip is being mounted in an array. Actually, we have the Seth just finished the prototype, and the point is attaching or connecting each one of those sensors in the transmit path so we can sample each one of the antennas and all of the couplings, and then basically treat the self-interference cancellation in the digital domain. And maybe I went too fast, so I think I have time for questions. Thank you so much.
All right, thank you.
It is super, yeah, it's super weird for me because I couldn't see anybody here.
No, thank you. Thank you. Nice talk. I guess I think we're actually right on time. So again, if you have questions, why don't you put them in the chat and we'll move on to the next speaker to keep things on schedule.
Okay, thank you so much, Randall.
Thank you.
Thank you.
All right. Next we have Bert Hochwald from Notre Dame.
Oh, hello.
Go ahead and let you share your screen and get started.
Yeah, let me see. How's that working for you?
Looks good.
So yeah, I'll be talking about the various one of the various projects that's going on within Wireless Institute that are related to SpectrumX, and it's radio mapping and how we're doing radio mapping and integrating into the SpectrumX platform. Let me just make sure I can move. So probably everybody knows this, but I'll go ahead just get everybody on the same page. A radio map, which goes by lots of different names, are basically spectrum characteristics over a region. And usually that means you picked some frequency or frequency band or some frequency and some bandwidth. You've picked the region and you're trying to figure out what's going on in that region in that band. And that could take on, of course, various forms, from as simple as just knowing, say, some sort of a power distribution, which I could say that simply, but even that is not that simple to get, to seeing what kind of actual activity and what kind of traffic is being sent over that spectrum. So just on this picture here, I have an example of a downtown Chicago map with some transmitters, and the signal power is given in the lower figure here, and then an occupancy map. Occupancy here telling you what is the signal level, where is the signal level over some threshold, in this case, minus 95 dBm. So mapping again, can take on a lot of forms. And in this particular case, we're looking at power, and we're looking at when does power exceed some threshold over some area. So they have as you can guess, they have a lot of applications. There's, of course, network planning, interference mitigation, dynamic spectrum access, including dynamic sharing, localization in the case where you're trying to find either a rogue transmitter, where you're doing site planning. This sort of thing is done by network operators and cellular providers on a regular basis. And of course, situational awareness, where you want to know, are there what is happening around you, and specifically in, say, defense-related applications, who's doing what around you in the radio spectrum, and of course the applications to electronic warfare. So it goes by several names: radio map estimation, spectrum cartography, prediction. They all have kind of subtle differences among them. I'm not going to try to really give you all the variations that are possible. Quite often it's done with some sort of a measurement campaign, can be time consuming and expensive. And a lot of the research today is aimed at lowering the measurement and or modeling burden. And very broadly speaking, the research falls into two main categories. One is emitter-based and the other is sensor-based. In the emitter-based scenario, we make some assumptions about where the emitters are, and we're trying to figure out a path loss. Excuse me, jumped ahead here. We're trying to figure out a path loss, and so our mapping is really about figuring out the path loss over some region. And the various metrics that we use are mean square error between a true path loss and some estimate. And the methods include ray tracing and empirical models and neural nets. The sensor-based approach, which is what we're favoring, uses not knowledge of the emitters, but rather knowledge of the sensors and the region. And so we're making measurements and we're trying to infer what's happening around us on the basis of measurements. And this is ideally in real time. So we would estimate rather than path loss, since we don't know where the emitters are. We can't really talk about path loss because that would imply that we did. But if we can just estimate power around us, not just where the sensor is, but in a large region around us, including regions where there are no sensors, then we feel like we've done a good job. So our methods include interpolation, dictionaries, and neural nets for that. In the emitter-based world, here's a kind of a summary of some of the techniques that are used. Various models for propagation, various tools, including commercial tools such as Forsk's Atoll tool that network planners use to try to figure out where they should place their base stations to cover a large enough area. And of course, a lot of the empirical models' advantages are that they're easy to use and interpret, but they really not good at capturing the full propagation environment. The neural network approaches can capture complex environments, but they of course suffer from the traditional things that neural nets do, which is extensive amounts of training and or data sets needed. And ray tracing is often used as kind of the it's ground truth as being probably the most accurate, but again, ray tracing is only as good as how much modeling you've done in the ray tracing and how sophisticated your physical and topographical models are. In a sensor-based approach, there's lots of different approaches within there as well. There's interpolation. And again, I won't go too much into the details, but here again, we're measuring things at a discrete number of sensor locations, and we're trying to infer what's happening around us with or without some specific knowledge of the emitters themselves. The interpolation methods are kind of pleasing in that you use things like radial basis functions and other types of functions to try to figure out, okay, I have a measurement here and a measurement here, so I'm going to smooth out and create some sort of a nice interpolated field between the two. But they tend to be very poor on resolution, and they tend to require a large number of sensors. Dictionary methods tend to do well when there's you can keep a relatively small number of path loss maps, so to speak, and then you combine these path loss maps together with the sensor measurements to try to interpolate what's happening between the measurements. They have their origin in things like compressive sensing and other optimization techniques. They require no training, and they can be used pretty effectively to figure out where estimators are. But again, they also require a relatively large number of sensors to be good and tend to generate relatively low resolution maps. So here's where we're headed. We're headed towards deep neural networks, and that's the approach that we're going to try to advocate for and integrating into our platform. Well, I won't give, there's a lot of references here, and there's also a lot of references at the end of the talk for people who want to peruse them. Basically, the neural networks have the approach that they are essentially very good at creating high resolution maps and also capturing details that physical propagation models have difficulty with. They also are very good at being trained on some limited number of scenarios and doing reasonably well when presented with a scenario that it hasn't necessarily been trained exactly for again. So although their training sets can still be large and it still be computationally expensive, it does something fairly reasonable when it sees something that it hasn't seen before. And model order estimation and these sorts of difficulties that are present in some of the other methods is just not there. So what are we advocating for? Well, I've given some of portions of this type of talk before in our setting. We're advocating for a method that uses very low number of sensors. You know, we of course have our own small sensors that we and lots of commercially available sensors that are relatively cheap that we can drop around all over the place. But we also want to be able to use the MEP or any other sensor that can be dropped and try to integrate all those measurements together to form a pretty high resolution map. And I don't have the time to go into the details of some of the pictures we have here, but we have a neural network approach that takes sensor measurements and converts this to an occupancy map that's pretty accurate. It's on the order of the mid 80s to mid 90s% accuracy with just a very small number of sensor measurements. And it does require some training over a region, but as I'll say in a moment, you can get around that too. So just to give you an idea of how we'd integrate this, what it would look like, we've sort of mocked up. It's part of this is mocked up, part of it is real. It's sort of in process. The way it would work is you would select a number of sensors, whether they're MEPs or other types of sensors. You say, here are the ones that we're going to be using. Collect the sensors. You are then that's selecting the sensors here in this page here. You would select the frequency of interest, your span, your bandwidth, and threshold levels, meaning what's the power levels you're interested in. You would do a scan. You would then select the region that you want to make the interpolation over. So you've selected the sensors in one step. You then select the region in another step, and the region and the sensors can be overlapping or disjoint. They don't need to be right on top of one another. And then make the map. Here I have a very primitive drawing of a map here over a room in a building here on campus. And what we're in the process of doing is supporting much more complex regions. What you saw here was an example of a neural net that was trained in free space. So if I don't have an accurate map of the region I'm trying to do my occupancy over, I might drop in a free space model, knowing that that's not really the right model, but it would give me a first cut at where things are occupied and where they're not based on the sensor readings. On the other hand, much more sophisticated measurements are also possible if we have inferences are possible if we have a sophisticated model, as this picture shows here. Anyway, I think I'm pretty low on time, so I wanted to stop there and say here's a large number of references for this, but thanks.
All right. Thanks, Bert. That was
Any
great.
questions that I can address, or is it too late for that?
There are a number in the chat if you want to
Want me to run through them real
address
fast, see if I
one.
can?
You could try to address one. I think we got about a minute.
Okay.
Sure.
Gosh, I have to get to them now. Let's see. One is through interpolation, is it possible to find the origin of the emitter? Generally, no. We found that that does not work well, because if you have two sensor readings, you don't necessarily know that there's an emitter between the two. That could be a high point in the reading. So interpolation tends to just smoothly interpolate between two measurements, and therefore doesn't have the cleverness to figure out there's something in the middle. How do these approaches accommodate temporal? So temporal dynamics are, the hope is that the environment does not change quickly, so that you've trained for an environment. However, you can infer very rapidly from sensor readings. So you can see the map update very quickly on the order of millisecond basis, as long as the environment doesn't.
Great. Why don't we stop there? I think
All right.
that was good. You got to my question, so you can stop. All right. And next up, moving on, we have Mike Honig from Northwestern. So go ahead, Mike.
All right. Hello, everyone. Let me, okay. All right. So I'm going to talk about, give an overview of the work that we've been doing on using beacons to coordinate spectrum coexistence among service providers that would otherwise be non-cooperative in the sense that was discussed in the earlier panel. And this is joint work with postdoc Swaroop Gopalam and previous postdoc Junaid Ozturk and co-PIs Randy and Dongning and Frank Lind. All right. So specifically, we're interested in the scenario where there's an incumbent, primary incumbent that wants to coordinate spectrum use with secondary entrants. And in general, this is going to require some signaling and feedback from the incumbent to coordinate this kind of spectrum access and to make sure that the interference is not excessive. There are a couple ways to do this. One is to make announcements about incumbent activity. This is the idea in the CBRS. They use TARDI S3 to do this. Our emphasis here is on using beacon transmissions, real-time beacon transmissions from the incumbent to notify incumbent activity and thereby manage interference. So this idea in general is not new, of course. It was actually proposed for TV white spaces to solve the hidden terminal problem. Beacons, I should use beacons in quotes because it's not quite the way we're using it here, but beacons are used in 802.15.4 to coordinate the networking. And more generally, beacons have been used to refer to really what I would say are pilots that are used to broadcast information and aid detection, for example, Wi-Fi synchronization, as well as the weak signal radio propagation protocol to aid detection in amateur radio. But our focus here specifically is on using beacons by the incumbent to coordinate spectrum access among secondary users. So that does not apply to some of the preceding applications, or this is different. And the applications that we're specifically looking at are coexistence with passive sensing, and in particular radio astronomy, and applying this idea to CBRS as well. All right, so the basic approach is shown here. That is, okay, so we have an incumbent transmitter and an incumbent receiver. Now, the incumbent transmitter and passive sensing, this could be radiation from a celestial object or a radiation from the atmosphere. And then we have an entrant transmitter that wants to share the spectrum, transmitting to an entrant receiver. And there may be interference, or there's likely interference from the entrant transmitter to the incumbent receiver. And then the idea is that the incumbent receiver will send a beacon to notify that the incumbent receiver is there. And the entrant then senses, so the incumbent receiver is transmitting the beacon in the direction of the incumbent transmitter. And then some of that, of course, leaks into the entrant transmitter, which senses the beacon and then measures the received power, and based on that received power, adjusts its own transmitted power to mitigate the interference to the incumbent. So we're exploiting channel reciprocity here. That is, the stronger the beacon measurement, then the stronger the inferred interference to the incumbent receiver, which means that the entrant transmitter should reduce its power or even shut off, say in the case of radio astronomy. All right, so the advantages of doing this kind of approach, well, it introduces a kind of coordination, which is useful. And it's based on real-time measurements as opposed to using static channel models. So we're exploiting channel reciprocity using these real-time measurements, and so thereby diminishes the need for these kinds of coarse channel or large-scale channel propagation models. It's dynamic, it's adaptive, it changes according to the environment. So in this sense, it'll improve spectral efficiency and utilization, again, relative to using static macro channel models. Challenges with this approach, though, which we're looking at. Well, first there's calibration. That is, we're assuming channel reciprocity, but then this may not apply to the hardware paths going in the two different directions. So that's one issue, analogous to calibrating an antenna array for transmission. Beacon placement, that is, the beacons is shown here. The beacon may not be exactly where the incumbent receiver is, and that's actually true for both the applications that I'm going to talk about, radio astronomy and CBRS. And this creates problems with reciprocity. This compromises the channel reciprocity that we want to exploit. There's also the challenge of designing the beacon, or the design, how you design the beacon in time, frequency, and space. That is, do you want an in-band beacon or out-of-band beacon? And, if there are multiple spectral lines, how closely should they be spaced in order to compensate for frequency diversity? Multipath. What's the duty cycle that's needed? How densely should the beacons be placed around the incumbent receiver? There's also a general trade-off between the overhead resources allocated to using the beacon and the estimation error. Here, estimation error refers to estimating the interference at the incumbent. And in important applications, the incumbent may not want to reveal its activity via these beacons, and so they may want to obfuscate their activities, and so you have to design the beacons with this in mind as well. So these are some of the main challenges. But in addition to the technical challenge, there's also the regulatory challenge, which I would argue is probably at least as important. And that is for example, if you look at passive sensing, the current assignments for passive sensing are rigid and non-transferable, which means these kinds of beacon-oriented schemes, you can't do this in the current regulatory environment. And furthermore, the current situation is that this creates an incentive for the scientific user to protect its assigned band. This is sort of analogous to this picture where the scientific user is defending the castle that is its own spectrum in the presence of these encroaching marauders, which are say the commercial service providers that would like to share or use that spectrum. This creates this kind of conflict, whereas really what you'd like is for the scientific user to have an incentive to actually trade, do some trading with the broadband service providers to benefit both parties. And one way perhaps to do this is to introduce flexible use rights where the scientific user maintains control of its band, but can negotiate with the entrant for constrained use. And so in this case, they can make a deal. They can coordinate activities using, for example, using the kind of beacon approach that I'm talking about here, where you negotiate the various interference thresholds. There's also the possibility of this kind of scenario then would allow the possibility for clearing additional spectrum that's allocated to other service providers to use that for passive sensing at certain times and locations in exchange, say, for sharing the bands that are currently allocated for scientific use. So more flexible use of the bands. All right, so I'll say a little bit first about passive sensing. Here's a scenario. We have a radio telescope, and this is the scenario here is to mitigate interference from these satellite constellations. So there's a radio telescope and now we have beacon transmitters that are placed, at the radio telescope or surrounding the radio telescope, and the beacons are transmitting in the look direction for the radio telescope. So actually, the picture is not quite accurate. The radio telescope should be looking towards, in the direction of the red arrow, but the beacons transmit in that direction. The satellites then listen periodically for the beacons, and if the beacon energy exceeds a certain threshold, then they just shut off because due to the assumption of reciprocity. So here, the challenge then is, or the issue then is how to design the beacon power, or you can adapt it to control the interference that the radio telescope sees by controlling the received beacon energies at the satellite. And this kind of scheme then can also be combined with broadcast updates that announce where the radio telescope is going to be looking, as well as quiet zones or no broadcast zones allocated in time, space, time, and frequency. So what you want to do then is make sure that the beacon energy, which is the beacon power times the integration time, is sufficient to guarantee that the interference at the radio telescope exceeds the threshold with a small probability. So this is a set of curves which illustrates this kind of relation, showing the probability that the interference exceeds the threshold versus integration time for a different number of satellites. All right, so moving on to CBRS. So the scenario here is that so there's the Navy, which operates radar, and there's the commercial users on the right-hand side. These are the CBRS devices, or CBSDs, this network of base stations. And currently, what happens is that any new channel request from one of the commercial service providers is managed by the Spectrum Access System, the SAS. And the SAS then coordinates with other Spectrum Access systems to limit the worst case interference to the incumbent. Now this is so this kind of resource assignment is based on large-scale propagation models, and this turns out to be computationally very intensive because you have to take into account where different locations for the mobile users, and this then creates large delays for coordinating these new assignments. In fact, up to 24 hours because of this computation and the coordination, and also you need large margins in order to satisfy this kind of worst-case interference constraint. So if we introduce beacons in this scenario, the idea then is, or the setup is that we have The naval radar is at sea. This is designated, say, by the protection area, the broad protection area. Then their commercial cellular network that's inland, and then we have beacons that are placed along the coast. Now, the beacons also function as sensors. So the sensors can be pointed outwards to detect incumbent activity. And then the beacons transmit, turn around, and then transmit inland to notify the base station, say, to lower their power or turn off. The challenge here is that first, the Navy wants to obfuscate its activities. So this means that the protection area may be is not going to be very specific. So there may be a large protection area here, and then the beacons are not going to be co-located with the incumbent radar as shown here. The beacons are along the coast, whereas the ships may be out at sea, and this compromises the channel reciprocity. So we've been looking at two approaches. One is to estimate the interference at the protection area based on the signal strength measurements at the beacons and sensors, and then to use the beacons to turn off the selected base stations. The other approach is that the beacons sense the incumbents and then transmit in the reverse direction, analogous to what the general approach that was shown on the first couple slides. And CBSDs, based on the beacon measurements, adapt their power and beam patterns based on the received beacon power. How am I doing on time? Am I a little bit over?
We're pretty much at time right now.
Okay, I'm going to have to skip. Okay, so let me skip through some of the details, but let me just show the one slide that a challenge in this particular CBRS environment is that you may have a ship here, a beacon which is, and you may have a CBSD here, which is relatively close to the ship, and another one which is far away. This compromises the channel reciprocity. And in this case, just to summarize what happens here is that you may need a threshold, a threshold for adjusting the power, which differs across the CBSDs based on, say, topological considerations or other side information. So that's one of the things we're working on. So I'm going to I'll skip this and just go directly to the conclusions and just say that as beacons can facilitate this kind of coordination between the incumbent and the entrance, it's adaptive, it's measurement based, and so in some certain situations there may be no need for channel modeling, but at least it mitigates the need for channel modeling. And we're addressing certain challenges like how do you design the beacon power, how do you do the beam steering, and how do you do the interference estimation. So since I'm a little bit over, I'll stop here.
All right. Thanks, Mike. I think you do have a question you can answer in the chat.
Let's see if I can see.
No, you can just answer it in the chat.
Yeah, okay.
And we'll go ahead and our next speaker is Nikos Sidiropoulos from Virginia. So Nikos, take it away.
Thank you. All right. Can you guys hear me and see my slides?
Yep, perfect.
All right. So I will talk a bit about our work on interference resilient communication. Brief summary of where we stand in terms of theory and progress in the last couple of years. And then I'll show you a video from powder, basically, a demonstration that we recently did on the powder testbed. So our work the last couple of years is geared towards communication in congested and contested environments. Two examples you can think of is 5G or Wi-Fi in places like Manhattan, or military communications where you might have to operate in the presence of jamming or other kinds of adversarial interference. So the basic idea first. So the question here is, how can we communicate reliably in the presence of an unpredictable and potentially debilitating interference, right? And if you see on the left-hand side, think of your signal as being the orange little vector S. We communicate using sequences. Sequences are vectors. Think of your signal of interest as being the orange little vector S, which is interfered by a strong primary blue vector P. What you will see as a result is a linear combination of S and P, and the weights of this linear combination will depend on the channel gains between the transmitter of the primary, let's say, interference signal, the strong interference signal, and your receiver, and then the secondary signal S and your receiver. So you cannot recover, the orange signal easily in this case. One thing to note is that if you have a second receive antenna, what you will receive is two linear combinations of the blue and the orange vector. So in that case, you will get 2 points on the PS plane. So what you can estimate then is the subspace, right? The span of P and S, but not S. So the real question here is, under these conditions, how can I estimate S, the orange signal? And the basic idea that we are using for the last several years is very simple, can be explained by geometry. So the idea is, if you have a repetition of your packet of the orange signal, right? You repeat the orange signal, but the interference does not repeat in lockstep with you. What happens then? Well, in the second transmission, you will repeat the orange signal, but the interference will have changed from blue to green. What you will get is 2 points on the subspace spanned by P2 and S. So in fact, you have two bases. You can compute two bases for two intersecting subspaces. And under very mild conditions, the intersection of these two subspaces will be aligned, will be proportional to your secondary signal of interest. So it's a very geometric proof a posteriori, right? If you have the insight, you can explain it this way. So by repetition, we create two intersecting subspaces whose intersection is aligned proportional to the signal of interest, and that is the basic idea. Now, when you took linear algebra, when I took linear algebra, we were not taught how you do subspace intersection, but the way you do subspace intersection is this equation down here towards the bottom of the page. You basically have two matrices, which are n by 2. N is the number of symbols in the packet. 2 is the number of antennas in this particular case. And you are trying to find two linear combinations of the columns of these two matrices that will generate the exact same thing, right? Because you know that by means of your repetition, the signal of interest is in the span of these two matrices, right? So this is this mathematical problem, which can be easily transformed to an SVD, thin SVD kind of problem, and can be solved optimally in time that is linear in the packet length and quadratic in the number of receive antennas. So you can actually compute this intersection, or the least squares intersection, and it is simple enough to make it to the lab. So a few years ago, we actually tested this idea in our lab using software radios. What you see here is one transmitter, primary transmitter, primary receiver. These are the orange, let's say, software radios. A secondary transmitter, secondary receivers. Because we have two receive antennas, we actually connect through a MIMO cable two single antenna software radios. And we tested this in the lab, and it works. And it has some really important benefits. So here are the key take-home points. This gives you a way to communicate effectively in this heavily interfered regime, where the interference can be very unpredictable and otherwise very hard to mitigate. The key challenge, if you're a communications engineer, in this setting, when you have an interferer which is potentially considerably stronger than you are, the key challenge is synchronization, but this repetition structure actually helps with synchronization as well. You can do blind synchronization based on the repetition structure. It can easily deal with carrier frequency offset, another important problem in in wireless communications, always there, right? And in fact, you can communicate reliably without estimating any channel, without any need for coordination between transmitter, receiver, and interferer. The channels can change from one packet transmission to the next. You can live with digital or analog primary and secondary. We have actually demonstrated with FM modulation as well. And it works no matter what the signal to interference ratio is in theory. In practice, I'd like to highlight two limitations. One is the practical limit is the resolution of your analog to digital converter at the receiver of interest. We use 12 bits in our software radio experiments, and that is enough to deal with interference in the order of 40, 45 decibels stronger than you. The price to pay is that you have a higher decoding complexity because you need thin SVDs, but this is manageable in many cases. It's higher, but not very high. Okay, so the original idea behind this goes back to 2022. We've made a lot of progress since then. We have generalized to multi-user and multiple access settings, for example, for IoT wireless networking protocols, together with Daniela Gabrich, published this spring in TWC. We considered a very natural synergy with hybrid ARQ. This was just published in ICAS 2025. You can actually get ARQ to cancel interference for you, which is very, very interesting. We just published a wireless communication letter on a multi-carrier broadband version of this. And we just submitted a paper on, in fact, it is possible to do this without the rate loss of repetition. That is sort of the freshest piece of work of the oven. But what I'd like to talk about for the rest of my time today is to show you a demonstration of this in the powder testbed. That was a special project that we carved out as part of the flagship Project One, together with Frank and Mary. And so we demonstrated already in powder, and we are doing a lot more experiments, both for the moment indoor and eventually outdoor. So let me play out the video so that I don't know how many of you are familiar with powder and what it takes to actually use that facility, that test bed. But it is an NSF supported test bed that allows remote use of radio equipment, and we've been using it for almost 6 months now. So let me quickly get to the video to make sure that you have a chance to see it. Let me know if you don't hear anything.
Hello, Boulder.
Spiros Pepas.
Today we're gonna have a demonstration of our method CCA, which recovers a weak user amidst interference. So we have an underlay weak user and a strong primary one. The power difference between the users is 30 dB, and we would try to send as an underlay weak signal an image. Here you will see the image that we are going to send. So here is the image that we are planning to send through the transmitter. And we're gonna use the Wi-Fi frequencies, 2.4 gigahertz. And we will use remotely the equipment that they have in the University of Utah. So let's see. Here we are at the point of view of the transmitter using the GNU radio. I'm gonna execute the transmitter, and it is gonna transmit the image that we seen at the transmitter, the building. This is the Rotunda, a very well-known building in Charlottesville. So you can see here with the blue is the image that is transmitted, and with the red one is a strong primary signal with QPSK symbols. You can see clearly that there is a 30 dB power difference between them. Now we go at the receiver. and we try to collect the superposition of the signals amidst noise as well. So you see, we receive from both the antennas. We have two antennas at the receiver. This is important for our method. You were able to see the received signals, the periodograms of the received signals. And now, since we received the data, we have to download them and run the decoding process for the CCA and recover the image that we have amidst strong interference. So give me a moment to move the files from the directory that I already have in the So I'm adding the first in the repository, the second, and then we have to check the status of the files. So we have modified the two files. And
I'm advancing a bit in the interest of time.
but we are playing in Wi-Fi frequencies, as I said in the beginning, 2.4 gigahertz. So we might experience, for example, interference from other signals that coexist. Now I'm pushing the files to my repository. And give me a second. I have to remove the previous that I had here.
So you have to communicate data through a GitHub account.
Yeah, and let's check if the files are uploaded. 1 minute ago, yeah, with the message that we tried, 3 dB interference image demo second try. I'm gonna download the FIFO files that contain the data streams that we received from the point of view of the receiver at the University of Utah. Now they are downloading. So I'm decompressing the files. Let me check. Give me a second. Decompressing again. Extract here. So FIFO1 and FIFO2 are the files that we're interested in. I'm copying the directory that the code runs, and now I'm going to run the decoding process in order to detect the image amidst interference. Here you can see the canonical correlation coefficient, which is maximized at the start of the packet, the first packet. We have created a protocol in order to collect in order the packets and reconstruct the image. So here you see that each recovered packet in QPSK symbols. So we have chunks of QPSK symbols that represent the part of the image at each packet. We have 50 chunks, so we are 35 right now. 38, 39, 40, 41. 49, 50. And boom. Here you can see clearly on the left-hand side the original image, and on the right the reconstructed one using CCA. It's almost perfect.
Okay, so in the interest of time, I will stop here. So what you saw was an actual demonstration of secondary transmission under a powerful interferer, which is 30 dB stronger. There were a few errors actually in the image, but they were hard to see by the naked eye. And the reason is that it was uncoded, right? So there were a few symbols who were in error. So that's all I had, and I'll be happy to take any questions.
All right. Thanks, Nikos. Great to see. Again, I think in the interest of time, we'll keep moving. I do know there were some questions you could look at and answer in the chat. Thanks a lot.
Thank you.
To our last talk this session, which is Mariya Zheleva from the University of Albany. So,
hi everyone. Can you hear me okay?
Yes.
All right. And now can you see my screen?
Yes.
All right. And now a question. I'm also chairing the next session. Do I still have 15 minutes or should I take 10 so that we can start with the next session in time? Currently and the future may are fighting right now.
I think we're fine to take all the time because the poster session's an hour and a half. So if we push a few minutes late, I think we can make up for it there.
All right.
Do you agree? Nick? No? All right, go ahead.
All right. Hi everyone. It's great to be a part of this meeting. So today I'm going to talk to you about some of our work on transmitter detection. What motivates all of this is what I want to spend a bit of time on. So as SpectrumX was unfolding, we were curious to see sort of and quantify what's the magnitude of the conflict. So of the spectrum conflict that is coming up. So what we did is we looked at sort of three broad categories of stakeholders: consumer broadband in purple, remote sensing, and radio astronomy. And what we studied was since the 90s and leading up to 2030, to the future, what were sort of the tunable ranges of those different stakeholders in the 0 to 50 gigahertz band, and also what were the instantaneous bandwidths that those technologies used. And so when I say consumer bandwidth or consumer broadband, this includes all the Wi-Fis and cellulars, and now up and coming the low Earth orbit satellite for broadband services of the world. And then remote sensing and radio astronomy were surveyed in terms of the most prominent remote sensing instruments and radio astronomy observatories in terms of their respective tunable ranges and power levels. And we looked for consumer broadband into the future by looking at World Radio Conference plan proceedings, and into the past by surveying FCC documents. And so the key takeaway here is that the conflict was very minimal in the 90s and early 2000s, predominantly because most technologies had small instantaneous bandwidths, so everybody could live in their own respective siloed range, and their tunable ranges weren't terribly large, especially for consumer broadband. But fast forward, a few tens of years, now we see a 1,000 times increase in instantaneous bandwidth for consumer electronics, and projected 10,000 times increase for some of the scientific users with up-and-coming instruments. And with that, it's worth noting that not all users are equally protected. So radio astronomy and remote sensing, even though they have large tunable ranges in which they can do science, they actually have very minimal designated bands, which were indicated here with those X's along the X-axis on the left-hand side. So minimal guarantees despite large tunable ranges. So with that, really the question that emerges here is how can we ensure equitable spectrum access with this ever-growing capabilities and demand, but across vastly different stakeholders and different and current protection guarantees. All right. Just making sure that this chat activity doesn't mean that you can't hear me all of a sudden. So with this, in order to be able to support this kind of wide-scale coexistence, we need to enable spectrum awareness, and more specifically, application-driven spectrum awareness. Because from application to application, what's required to be measured and the insights the different applications require also vary quite drastically. And just a few examples here. If you look at those broad stroke applications such as spectrum sharing technologies or spectrum enforcement, ensuring user privacy and security when collecting spectral data, or making sure we create agile policies, all of these applications can ask quite different questions that engage with the underlying pipeline in terms of how analytics are performed and how data is collected quite differently. But all of them sort of point to the same need of being able to understand in detail the spectrum use and other granularity of individual transmitters with time, frequency, and space as underlying degrees of freedom. All right. So this sort of underpins the spectrum measurement ecosystem in which we've looked to position our spectrum awareness research over the years, and SpectrumX has served as a catalyzer in grounding this research increasingly in reality. So the spectrum measurement ecosystem, we think about it as comprised of some number of physical components, most definitely transmitters, or more broadly, spectrum stakeholders that may or may not be actively transmitting that we're looking to be aware of. Then some sensing front ends that are going to help facilitate data collection for this awareness, cloud-based backends that are going to be collecting the data. And on top of those physical components sit a number of functional components and data flows that help us, ultimately make use of the physical environment in order to create some intellectual understanding about it. Those functional components include spectrum sensing. So what drives what kind of data and for how long and across what degrees of freedom is this data collected? Spectrum awareness that creates an opportunity in broad strokes for us to understand what's occupying the spectrum and what is it doing over time and frequency and space. Transmitter tracking, meaning if one of the multitude of observed activities is of increased interest, to be able to hone in on that activity and further profile various aspects of it, and data presentation so that various applications can actually make use of the insights. And an important but oftentimes overlooked component between sort of the bridge between those physical and functional components is the data context, or what we often refer to as metadata. And we've thought about metadata in my group as sort of this, peels of an onion. So as you go through the functional components of the pipeline, you add increasingly the context of how the data came to be. At the spectrum sensing step, important things to consider are what's the quality of this data and how do you even begin to characterize the quality and whether it's going to serve a particular task? What was the sensor configuration, so how the data was collected? But also very importantly, what was the environment when the data was being collected? So you can contextualize it with respect to what was happening in terms of noise floor, in terms of where the sensor was situated and what propagation environment might it have been subjected to. And what target signals, if anything is known, were available or were being targeted. And so that starts to sort of facilitate ground truth establishment with the data. And then as this data travels from left to right through the pipeline and being processed for spectrum awareness and for transmitter tracking, additional metadata is being added to further contextualize how the data was used, what models and parameters were employed, what algorithms, and what was the performance observed. And so those together can now more intelligently facilitate spectrum applications from spectrum policy through those technologies, spectrum sharing technologies, enforcement, and user privacy and security. And so in my lab, we've played through this pipeline across various points. SpectrumX has served as a catalyzer in really honing in on problems that are of practical importance and developing algorithms that have higher potential for practical impact, and has also facilitated this cross-disciplinary conversation that started to happen in a single PI. And also, through the flagship Project One, something that a single PI or a small group could not lift is around the implementation of a data framework that actually now has the potential to bring in those disparate components that have come out from research into something that's whole and alive. So I want to focus on just one piece of work that has come out over the last year that really focuses on spectrum awareness in challenging scenarios. That is a paper called SCAN, Sparse Recovery Transmitter Detection, that will be presented next month at InfoComm. And really the credit goes here to my student, Blessing Okoro, who is in the audience, and he will have a poster on that tomorrow. So if you want to learn more about the details of the framework, I very much encourage you to go and visit him at his poster. So the goal with how we approach spectrum characterization for awareness is to basically be able to characterize the dimensions of each piece of spectrum activity in terms of its bandwidth, in terms of its duration and interarrival time, and then also be able to reconcile individual blips of activity into a longitudinal transmitter pattern. So be able to tell, in other words, this amount of blips came from transmitter 1, this amount of blips came from transmitter 2. And this is important because on one hand, it can help facilitate really finely granular spectrum analytics. And then on another hand, can help with applications such as transmitter classification, especially in low SNR regimes where those classification tasks usually tends to fail. So detailed characterization, such as what I'm about to describe, can help lift up signals from the noise floor and then aid in subsequent classification. So really, the goal here is to be able to characterize across various coexistence scenarios, including in challenging scenarios such as the right-hand side, where transmitters might be interfering, so fully overlapping in terms of time and or frequency, where some of the transmitters may be narrowband and short-lived, such as radars and CBRS, and where activity may be observed at really low signal-to-noise ratio. So why is this hard? It is hard because the state of the art largely thinks about transmitter separation in terms of power levels, and where transmitters tend to be of similar power levels, we cannot separate them, as shown in the left-hand side here. And so this really underscores the need to not only be power aware when we go to perform spectrum analytics, but also to be spatially aware within the two-dimensional time frequency space in which activity is observed. Furthermore, existing work is really challenged to detect short-lived narrowband transmitters that result in minimal spectrum activity. And usually those detections are overtaken by, especially in the face of interference, are overtaken by detecting the long-lived prominent transmitter, whereas short-lived activity, kind of falls behind. So the key intuition behind what we're doing here is, first of all, we observe that despite the fact that it is noisy and hard to discern, spectrum data is actually sparse. So we can exploit the sparsity in order to be able to represent originally low SNR and noisy spectrum data as fewer components of interest. And we do that through a sparse dictionary coding framework. So what sparse dictionary coding does is it essentially allows us to represent an input data as a combination of fewer basis elements from a larger predefined set that is called a dictionary. So effectively, this dictionary representation seeks to create an alternative representation of the input data in terms of a linear combination of some number of dictionary atoms. And you can control essentially the sparsity of representation by enforcing sparsity constraints that can effectively control how much of the detail from the original trace you're willing to consider in your analytics. So effectively, this boils down to the optimization that's shown here at the bottom left-hand side of the slide. All right. In this case, we're dealing with multidimensional, so particularly two-dimensional data of spectrum activity over a particular frequency span and over time. So what we're exploring here is multi-dictionary sparse coding that allows us to represent the temporal and the frequency activity observed in a particular scan as one rank factorization or rank one factorizations of the temporal and frequency activity. This helps create cleaner interpretability of the data in terms of time, frequency, and now, not in this work, but sort of as a sequel under the flagship Project One, we're adding spatial constraints as well within this consideration. So effectively, we modeled the observed signal or spectrum scan as a mixture of some number of transmitters and noise and factorize them as shown here. All right, so I only have 1 minute.
Okay, yeah, 1 minute to wrap up.
Really, I'm going to take this minute to invite you to Andrew's poster tomorrow. Where you'll be able to see a lot of results, including from some of the over-the-air experiments that we've done, which I was planning to highlight here. But so with that, to wrap up, we conceptualized this notion of detailed transmitter characterization. We design SCAN, which is unsupervised and can work for any arbitrary band and transmitter behavior. And the demonstrated performance is high and consistent across various challenging scenarios, including with interfering short-lived and narrowband transmitters. So with that, I don't have time for questions, but I'm happy to answer any in the chat.
All right, thank you, Mariya, and thanks to all of our speakers in this research session. I think, given 5 academic speakers and we're only 5 minutes over time, that's remarkable. I will turn it back to Nick.